All right, let's get started. So we'll do some coding and I'll let you do some coding as well. And then I'll solve it here. So this is not working. It's off. All right. What I'm going to do is I'm going to use the mesh from PL6, but I will not do the elasticity problem because we haven't covered that in class. And I had the choice of whether we would do the next theory. In the syllabus, I said that I would do the beginning of elasticity, but I actually want you to do more coding. So we'll do more coding. That's the fun part of the class, no? All the coding. Let's see, are you not working? Yes. So what problem are we going to do? The mesh that I saw in the for PL6 is this ring mesh with quadrilaterals. There's a bunch of quadrilaterals. You have to download the mesh. But instead of solving the elasticity problem, we are going to solve a heat transfer problem. And then I think the way the mesh is labeled, I think the nodes at the beginning are these ones. I think those are the first nodes. We can check, but I think these are the first labeled nodes. So in order to do the matrix partitioning system, I will just treat those as the ones with the essential boundary condition. So any value of temperature that you like? 50. All right, so we're gonna have 50 for those nodes. And then for the other boundary, let's just do no flux boundary so that I don't have to explain how to get the flux vector. So all of that, we're gonna just do UN equals 0. So no flux, that makes it a lot easier. And then we need the conductivity and the source term. So I don't know, value of conductivity, 3. And then for source term, do you want a constant source term or do you want a function? -5. I wonder if we're gonna get some negative temperature. -5. Okay, we'll do -5. I kind of want to do well, it doesn't matter. We still need to do gas quadrature. So -5 is okay. We can do because it's quadrilaterals, even if it's constant, we cannot just do the integral. We'll do it with Gauss quadrature. I'll actually change it. I'll do -5x. So it will be some positive. So it will change, you know, there's a source term, but it changes from left to right. So -5x. Okay, so that is our problem, and that's what we need to solve. Find the temperature for that problem. Before we jump into the code, as you can recall, for any heat transfer problem, any finite element problem, we are going to have our usual for loop. And actually, I will let you struggle a lot. That's me, huh? But I'll go around and help you. But we're gonna have for loop over elements as usual. Right? Then in that for loop, we need to get the, you know, for I in elements, we need to get the nodal connectivity. So, you know, we need node 1 is gonna be reading the elements I comma 1, and then node 2 is elements I comma 2. So this one is reading from the element array, which 4 nodes make up every element. We're gonna read the nodes. Then we're gonna read, given those node values, we're gonna read the X and Y coordinates. So X, for example, is in the node X array, the N1, and this is a vector. So it's gonna be a NumPy array. You can either read the whole vector. If you want to split it into the X and Y coordinates, you can just do not the array, but you can split it into node X and 1 comma 0 would give you the X component. If you do node X and 1 comma 1, it will give you the Y component, whichever you want. So this one would be as a NumPy array. If you want to get the whole vector, you just read node X and 1, for example. Or if you want to get the components, you can read the components. And obviously you can do that for every node. So node 2 is node X and 2, and X3 is node X3, and so on. Well, I'll just write the last one. There's 4 nodes, so. Okay, so reading the elements, reading the nodal coordinates. And that's all we need to then assemble the stiffness matrix. So we will need to calculate the stiffness matrix and the force vector, right? That is our goal, is to calculate the stiffness matrix and the force vector. Now, what is the stiffness matrix? The stiffness matrix is the integral, is a 4x4 matrix because there's 4 nodes, and it has the combinations of the gradients of the shape functions. So for example, the first one is the integral of the conductivity times the gradient of shape function 1 times the gradient of shape function 1 integrated over the quadrilateral. The second one is gonna be the integral of gradient of shape function 1 times gradient of shape function 2, and so on. So basically all 16 combinations. For each of these, we have to do it with Gauss quadrature. So this integral that we need to do, we're going to do it with Gauss quadrature. So what is it going to be in the end? It's going to be a sum over the integration points. We can use reduced integration if that, it doesn't matter if we do reduced integration of the 4 points. Reduced integration will be just evaluated at. So reduced integration will be just evaluated at psi eta 0, 0. 0, 0 for reduced integration. So that will be a single evaluation. And if we want to do the full integration, then we need these 4 points, which are, you know, minus 0.57, minus 0.57, and so on. This is 0.57 minus 0.57. And the other one is 0.57, 0.57, and the last one is minus 0.57, 0.57. Anyway, so we're gonna loop over the integration points, and then need to multiply k, need to multiply the gradient of the first shape function at that psi IP eta IP, and need to dot product with the gradient at the corresponding psi IP eta IP, and then the weight of the integration point, and then the determinant of the Jacobian. That's the Gauss quadrature. And there's two things that I still need to tell you what they are. They are, as usual, the Jacobian. What is the Jacobian? The Jacobian is this matrix that will have the sum of the partial derivatives with respect to psi, the sum of the partial derivatives with respect to psi of the y coordinates, the sum of the partial derivatives with respect to eta of the x coordinates, the sum of the partial derivatives with respect to eta of the y coordinates. That's what the Jacobian is. And the gradient with respect to x of the shape function is going to be the inverse of the Jacobian times the gradient of the shape functions with respect to psi. I'll expand this a little bit. This gradient with respect to psi is just dn1 d psi, dn1 d eta. I know it looks complicated. I'll help you. I'll go around and help you. And you can work in pairs. That makes it easier. And lastly, for the force vector, we also need to do Gauss quadrature. The force vector is going to be the integral of s times the first shape function, the integral of s times the second shape function, the integral of, so all of that 4/1. So integral of s times each of the shape functions. Gauss quadrature means sum for the integration points between 1 and 4. S evaluated at x, evaluated at psi IP, eta IP. Then first shape function evaluated at psi IP, eta IP, the weight of the integration point, and the determinant of the Jacobian. And the Jacobian is the same. Questions? Right. Well, let's do it in parts. I'll give you 10 minutes. I'll go around, help you a little bit, come here, do a little bit of the code, and then hopefully we'll have another 10 minutes for you to work, and then I'll come back and work on the code. But we'll use the sequence of that code there, the reading message code there. The first for loop, that's the for loop of the one and two code there. The number of things that the speed of the We make use of the columns as the gradients. In this case, not the what? So the columns will be the gradients of the shape function with respect to x. So you need to. Because the gradients have the 1/2a. So every column has the 1/2a, so that one just got pushed back. Yeah, like the actual gradient in the triangle was in y2 minus y3 over to a x2 minus x3 over to a. That was part of the gradient, but because every single entry has the same, it's got out. But in general, every column is the gradient with respect to x. Yes.
That is, should be already PL6. Go down. That's below. Because this should only be the part of the program. But it's below, this is just probably the back. I think here, this is the part. This is exactly this double red. And then these elements array is an array that basically says for each quadrilateral, what are the four nodes that make up this quadrilateral, right? And so in these loop over elements, I need to go and say, the first time in that loop, for element 0, what are the four nodes that make up that element? So these four values. And for the first element, that might be 3, 5, 16, 21, right? And then the next time in the for loop for element 1, what are the four nodes that make up element 1? And that might be, I don't know, 2, 4, 1, 0, something like that. And then that's it. So every time in the loop, you're gonna get for every element, what are the four nodes that make up the element? And you need those values of the nodes because then you use these values to go and get the x and y coordinates. Gotcha. Right? Because again, for element 1, yes, that should work. Maybe it's the file is not uploaded.
I was just messing around with the CD. Trying to understand.
But yeah, that one you don't need to worry about. It's just gonna read the mesh, and all it does is create these two arrays. Right. One array which has the node, yes, and all the XY points, and one array that has for every element, what are the four nodes that make up that element. So that's basically what it's done. It's just reading the mesh, and it's really good.
Is that what this puts the nodes in each element?
I mean, it's just reading it. It's in a file. So if you open the file, you will see first a list of XY coordinates, a long list of XY coordinates, like 500, not how many. And then after that, there's a long list of four numbers, which are the nodes that make up each element. But that's already on that text file. If you were to open the text file, you will see. Yeah, exactly. So these are all the XY. So there's 500 nodes. These are all the XY points. And you scroll down. Then it says how many elements. Yeah. Before this, there's like element 9. And you just say, okay, there's 500 elements, and every one of these lines is what are the four nodes that make up.
It corresponds to one of these.
Yes, like for example, the first 0, 12, 1, 3, 4. So that means that the coordinates would be the 0, right? Then the 12 rows and the.
Gotcha.
And that basically defines your base.
Okay. Yeah, that makes sense.
Yeah, so those have these two things, but that should already be full.
Right, yeah, I was just wondering.
Going.
And we do that there are many
I mean, yeah, the solo is good.
yeah. So how do you like all big vector find basically like I want to get the first column out of it.
Did you do the thing?
Yeah.
Then you don't need to do big transport and big.
Oh, that's it.
The big transport and big is basically doing all the doctor times. We haven't made the device. Smart vision. I feel like we lose the
Yes. We can sell one.
No, that you it shouldn't be, it should just be n naught and n. That's why the elasticity is like, because you have x and y components.
Should I change this or?
Yeah,
Okay.
it should just be n naught and.
Okay. Yeah.
All right, let's give you a little bit of help. Let me find the. Actually, just don't. All right, let's give you a little bit of help. So let's do the stiffness matrix for heat transfer for quadrilateral elements. Just read the mesh, this part, just read the mesh. The shape functions, just need to run that. If you want to plot something, this I think is just plotting the x coordinate. And now this is the fun part. So for the stiffness matrix, what is the size of the stiffness matrix for the heat transfer problem? Hopefully you're not looking at the elasticity one because that one is different. So this one should be number of nodes times number of nodes. Just see if I have it as n nodes or n, yeah, n node. And the force vector is just going to be n node. This for loop is what I had already sketched out on the iPad. So that one stays the same. And then reading the x and y coordinates, that one just stays the same. Now integration, I guess I said single point so that we don't do a for loop. Otherwise, you would have to do all 4 different combinations of psi eta, the minus 0.5, 0.5, and so on. But if you do reduce integration, then the only one that we need to evaluate is at psi eta equals 0, 0. I saw some of you were already doing this. This is what is the isoparametric map. Evaluate the shape function at the corresponding psi eta times the nodal value, and it's a sum of. So here you just get sum of, sum of, sum of. So hopefully this part is correct. And then for the y coordinates. Then for the Jacobian, I don't know if people got to this one. Yes. So this one is again just sum of, but instead of the shape functions, the derivatives of the shape functions. So this is just going to be sum of dn1 d psi, dn2 d psi, En3 psi, En4 psi. For eta, it's same, but with eta. So derivatives of the shape functions with respect to eta. Times the corresponding x and y coordinates, and then for y is the same, but with y coordinates. So this one is sum of the derivatives of the shape functions with respect to psi times y coordinates, and the last one is just sum of the derivatives of the shape functions with respect to eta times the y coordinates. And those are the four entries of the Jacobian that I had in the slide, well, in the iPad. And then we just need to ask NumPy to get us the inverse and the determinant. Any questions about this? Evaluating the isoparametric map and evaluating the Jacobian. All right, so we have the isoparametric map, the Jacobian, the inverse of the Jacobian, the determinant. Then we don't need to do with the B matrix, but we need the gradients with respect to x, y. These are the gradients with respect to psi eta. What is the gradient with respect to x, y? What should I have here?
Multiply the gradient psi eta by the first.
Correct. MP dot J inverse times the gradient psi eta. Again, so we have the isoparametric map, the Jacobian, then we got the inverse of the Jacobian and the determinant. And with that inverse of the Jacobian, we can transform gradients with respect to psi eta into gradients with respect to xy. All we do is multiply by the inverse of the Jacobian. I mean, that's really all the information that we need. This we don't need, this is for elasticity, so I'm gonna delete that. Now, what is the stiffness matrix? This is, I'm gonna skip this B matrix because the B matrix is just a more efficient way of getting the stiffness matrix. But what is the stiffness matrix as I wrote it? The first entry is the sum of the K. I need to define what the K is. So K, we said, I think I forgot what we said for K. What did we say for K? We said 3. So is K times, if you go back to the notes that I was doing there, times the weight of the integration point. This is a single integration point, and in this case, the weight is 4. That one I know, but that one is from table. For the reduced integration, the point to evaluate is psi eta equals 0, 0, and then the weight of the integration point is 4. So I have K times the weight of the integration point times the determinant of the Jacobian times the first entry is gradient N1, gradient N1. So that would be just MP dot gradient on F of N1, gradient on N1. So for example, this is not zeros, MP, let me do array. So this is the first entry. So K times the weight of the integration point times the determinant of the Jacobian times the dot product of gradient N1, gradient N1. Then the second entry, there's 16 of these, which is a little bit annoying. But the second entry would be the same, but the dot product of N1 with N2. Then the third one would be the dot product of N1 with N3. I don't want to do all of them, but I'll do all of them. And then grade everything, but the only thing that changes is which dot product we're doing. Any questions about that? There's a more efficient way of doing it. I'll do it with the B matrix. So I'll do it with the B matrix. But the nice thing though is that it's a lot of copy pasting. So that is the first row. What is the second row? The second row is everything, but instead of N1s, this is going to be N2, 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 N2. The third row is everything with N3 at the beginning. And then the last one is everything with N4. Any questions about conceptually? This is the same that was written in the by hand. It's just the dot product of the different combinations of the gradients of the shape functions. Is there a more efficient way of doing this? Yes, with the B matrix, but I haven't really emphasized the B matrix a lot. So what you can do is make this B matrix where the columns are the gradients. So the first column would be the gradient of N1. The second column would be the gradient of N2. The third column would be the gradient of N3. And the last column would be the gradient of N4. So if you do that, then the stiffness matrix is going to be the BE transpose times BE. So that's a little bit more efficient, but either way is fine. This B transpose B is doing the exact same thing that I'm doing. I'm writing out all 16 entries, but the B transpose B would do exactly the same. Questions? And we have a single integration point, so we are not adding things. If this was the full integration, everything here would be in that one. If this was a full integration, instead of just the single psi eta, there will be a for loop here. So there will be a for loop where you would have, you would need to get the different combinations of psi eta. So the first time in the for loop, you would have psi minus 0.5, eta minus 0.5, and so on. So then you would have to repeat this 4 times. But, for reduced integration, we only need, there's no for loop, we only do it once. So questions? Yes, it's right here. So K, the weight of the integration point, the determinant of the Jacobian, and then the dot product. Yes, yes, good. That's a good one. Yes. You still need to add the K. And you still need to multiply by the weight of the integration point and the determinant of the Jacobian. All right, for the force vector, before I run out of time, we said S was equal to, ignore this because this is for S equals either minus 5x or minus 5. But minus 5x, we have the x interpolated here. So minus 5x, and then for elasticity is going to be 8/0, but for the heat transfer problem is just 4 components. And then is basically the weight of the integration point times the determinant of the Jacobian times whatever we need to integrate, which is just S times N1 again, if this was multiple integration points, we would have a for loop, and then we would just continue to add for the different integration points because it's just a single integration point. There's no for loop. And then the entries are just, they all use S. The only thing that changes is the shape function. So either integrating shape function 1 times S, shape function 2 times S, shape function 3 times S, or shape function 4 times S. Questions? And then I'll ignore this one. We need to do the assembly. For the assembly, you can do all 16 rows. Right. What is the assembly? You have done this before for the triangles. You know that, for example, for I think you had this type of row in the past, where every single entry of the KE goes to an entry of the K matrix. So, 0 maps to node 1, 1 maps to node 2, and so on. So the next entry would be, 0, 2 would be node 3, and so on. But you would need 16 lines to do that. So if you don't want to write the 16 lines, you can do it in a couple of for loops. Just do node map NI, node map NJ plus equal KE NI and J. These 4 lines, of code, well, let me remove that, but these 4 lines of code are the same as if you were to write all 16 entries. And for the force vector, and then that's the last thing that I'll do, you can just do the same. These 2 lines is the equivalent of 4 lines. This is basically replacing, instead of doing F node 1 plus equal FE0. In 2 lines, I have those. The assembly. And that's it. Questions? I want, so yes.
When you call node map NI, doesn't it bring a vector on a single line?
No, node map NI, it either gets node 1, node 2, node 3, or node 4. I promise it works.
But each node has two values.
No, node 1 is just, the node is just the number. Right? The X and Y are 2 numbers, but the node is just the number of the element of the node. It is a single value.
That makes
All right. I'll see you on Monday.
I wrote yesterday.